Welcome to my video course on mastering ERTMS/ETCS signaling systems. Today, we're diving into the absolute pinnacle of modern railway signaling, ETCS Level 3. Now, if you've been following our earlier breakdowns, you already know that Levels 1 and 2 completely transformed train control. But Level 3, it literally rewrites the rulebook, stripping away billions in legacy infrastructure and pushing network capacity to its absolute physical limit.
Here's a quick look at our agenda. We'll start with an introduction to ETCS Level 3, followed by the moving block concept, then virtual block sections, and finally, ensuring train integrity.
Let's kick things off with Section 1, Introduction to ETCS Level 3. Let's define exactly what this represents in the evolution of modern traffic management. Traditionally, as you probably know, train routes were cleared in fixed physical track sections. Picture a static block of track, maybe 2 kilometers long, where only one train could be inside that block at any given time. That was enforced by trackside signals and track circuits. Sure, it's safe, but it's highly inefficient because it leaves these massive gaps of empty track. Well, Level 3 fundamentally shifts away from this by implementing full radio-based train spacing. We are entirely ditching the reliance on those physical, static blocks and stepping into a dynamic, highly responsive system.
That departure from fixed sections brings us to Section 2, the moving block concept.
So instead of waiting for a train to clear a huge fixed section, Level 3 implements what's known as absolute braking distance spacing. In plain English, the system calculates the exact distance needed for a train to stop safely, based on its current speed, and it creates a virtual moving block that continuously travels with it. Think of it like a protective bubble that physically travels down the track with the train, instantly expanding and contracting in real time based on how fast the vehicle is moving.
To see how this bubble operates in practice, let's look at the safe braking protection curve. The onboard system is continuously monitoring the train's data, crunching the numbers for the maximum safe speed instant by instant. It ensures the vehicle can always stop safely before a target point, which, in a moving block system, is basically the rear end of the train directly ahead of it. If the actual speed ever breaches this calculated curve, the system doesn't wait around for a human driver to react, it automatically hits the brakes to guarantee a safe stop.
For network operators, this is a real game changer. By dynamically updating this braking curve, the moving block shrinks train spacing down to the absolute minimum safe distance required to stop. This maximizes line capacity. You can safely run significantly more trains on the exact same physical track, vastly increasing your overall throughput without having to pour concrete for new rails. It is a massive advantage for high-capacity networks trying to squeeze every ounce of utility out of their existing infrastructure.
Moving right along, let's jump into Section 3, Virtual Block Sections, the technical magic that makes all of this happen.
This is where we see a radical shift from infrastructure-heavy detection to vehicle-led detection. Instead of relying on physical hardware installed continuously along the rails, the system uses radio-based train spacing to create these virtual blocks. Trains actually determine their own precise position using onboard odometry sensors and reference beacons, and they continuously report this back to the radio block center using the railway's dedicated communications network, GSM-R.
Because the train dynamically figures out and reports its own position, the railway no longer needs legacy fixed track release devices. Those expensive, high-maintenance track circuits and axle counters, they're completely eliminated from the trackside, which represents immense operational cost savings. The train just finds its exact position using its own sensors, treating passive positioning beacons, Eurobalises, purely as electronic milestones on the ground to correct any minor distance measurement errors.
But this introduces a really fascinating engineering challenge. If the track infrastructure isn't physically detecting the presence of wheels on rails anymore, how do we confidently know the track is actually clear behind the train? What happens if a wagon physically detaches from the back of the consist?
That crucial question brings us to Section 4, Ensuring Train Integrity.
Because the track infrastructure is no longer acting as a physical sensor, the train itself must take over this critical safety function. This is known as train integrity, the vital continuous confirmation that the train is fully intact from the front locomotive all the way to the very last carriage, verified directly on board. The vehicle itself literally becomes the ultimate guarantor of its own completeness. This internal monitoring is totally non-negotiable and has to function with flawless reliability. It guarantees that absolutely no part of the train consist has detached and been left behind in a virtual block.
The central system relies entirely on this onboard confirmation before safely clearing the space for the next approaching train. If integrity is lost, or the system even fails to confirm it, the virtual block remains locked down tight, ensuring no following train can ever enter that space.
To wrap up, ETCS Level 3 represents a brilliant leap forward. It maximizes capacity through the dynamic mathematics of moving blocks while relying on vital onboard train integrity to ensure flawless safety. It's a masterclass in doing more with less, pushing railways into a truly digital future. But it leaves us with an interesting question to ponder as we look ahead. As trains become entirely autonomous, self-reporting entities, how will this massive shift in control reshape the role of the human train driver in the decades to come? Thanks, we can see you next video.